Good afternoon, everyone, and welcome to the Nuclear Waste Services Research Support Office's annual webinar from the Advanced Manufacturing discipline. My name is Steve Jones, and I'm Professor of Joining Technologies at the University of Sheffield and Research Discipline Lead for the Advanced Manufacturing theme within the NWS RSO. My colleague, Mr. Richard Hardy, subject matter expert for the NWS RSO, and I will be chairing today's webinar, where the presentation material will be covering subjects such as canister design, manufacturing and modelling, a non-intrusive inspection technique for nuclear applications, and gas evolution associated with unshielded intermediate level waste. We're naturally extremely pleased to have Dr. Steve Dodds and his colleagues from TWI, who will be sharing with us some of the work they've been doing in developing, modelling and manufacturing nuclear canisters tolerant to a 100,000-year breach. And also two PhD researchers, Miss Arij Asad from the University of Bristol, who will be presenting her work on ventilation of hydrogen in unshielded intermediate level waste vaults, and Mr. Matthew Riding from the University of Strathclyde presenting some of his work on laser inspection for nuclear applications. However, before we commence the presentation, just a few courteous housekeeping points, if you wouldn't mind. Number one, could you kindly keep your microphone muted and turn off your cameras to improve bandwidth and minimize background noise? Could you also please log your questions in the chat rather than raising your hands, and we will try and refer to all these Q&A in the session at the end of the webinar. And naturally, where we can't get around to answering all those questions, we would follow these up and definitely engage with those people who have actually asked for those questions to be answered. And finally, we are planning to record this meeting. It's currently being recorded, so please inform us if this is unacceptable to you, because it's naturally part and parcel of sharing information. So before we start these presentations, Richard and I will spend a few minutes providing a brief background to our discipline to set the scene for the upcoming presentations in support of the GDF. So thank you. So what you'll see on your screen here is our advanced manufacturing research taxonomy. So advanced manufacturing is one of the 11 disciplines critically needed to deliver the NDA's GDF program. So it's no surprise that this discipline requires strong interconnectivity with all other 10 disciplines to deliver its objective of producing sustainable waste management systems imperative to closing the nuclear life cycle, and obviously making nuclear, where possible, a cost-effective and environmentally acceptable energy vector. So this slide that you see here is our advanced manufacturing taxonomy presented to show the array of strategic research strands within each critical engineering theme. And our webinars are prepared in a manner to highlight research that has been or is being done within each strand. Those in amber highlight our last webinar content, and those bounded in red are highlighting the areas that our speakers will be discussing today. Today's presentations will show some of the essential research work on the journey to proving the structural integrity of disposal systems, while safely mitigating gas evolution within the GDF's infrastructure. So my colleague Richard will now provide a brief introduction to the NWS. Thank you.
Thank you, Steve. Good afternoon, everyone. As Steve says, I'm Richard Hardy. I'm a Senior Engineering Manager in the engineering team at Nuclear Waste Services. We're responsible for delivery of a geological disposal facility for the UK's higher activity waste. GDF, as we call it, is an engineered facility for disposing of higher activity waste in suitable host rocks between 200 and 1,000 metres below the surface. We're currently in the process of finding a suitable site with a willing community in line with government policy, and we're working with community partnerships as part of this process. So in this slide, we can see just a schematic of the facility itself, which has both surface and underground areas. And in the UK, we categorise high activity waste into two broad types, and that's high heat generating waste and low heat generating waste. The high heat would be waste such as spent fuel and high level waste from reprocessing of spent fuels. The high heat generating waste for the UK inventory is lower in volume, but it has the majority of the radioactivity. And as the name suggests, the heat it generates needs to be considered in its management. And we do this by spacing out containers in disposal tunnels. And this effectively dissipates the heat into the surrounding rock. Therefore, it could take more footprint in terms of the size of the underground part of the facility. Whereas low heat generating waste, which includes materials from decommissioning and materials that have been in close proximity to the fuel, is greater in volume, it can be disposed of by stacking more closely together in disposal vaults.
Oh, hello.
We
Hi,
go
is
to the
he
next
sitting there?
slide, please.
Yes. Hi, baby.
We've got a little bit of background noise. If you could just mute, please. Thank you. So this disposal concept differs too between the two. So more emphasis is placed on container longevity for high heat generating wastes, and completely sealed containers are likely. Whereas low heat generating wastes have more emphasis on other parts of the multi-barrier system, things like the waste form and the surrounding backfill, and have less emphasis on the container. So containers are vented to allow gases to escape prior to closure of the GDFs. There's that clear distinction between the two. We're obviously going to hear from TWI and their work with NAGRA, our Swiss equivalent, on their high heat generating waste on sealing of those disposal containers. And later we'll hear from Arij from University of Bristol on management of gases from those low heat generating waste containers, which are vented. Thank you.
Thank you, Richard. Thank you, Richard. Thank you very much. So this is what we're all here to witness today and understand a little bit more. So I would like to introduce our first speaker, Dr. Steve Dodds from TWI, who will be calling upon further TWI colleagues to support this presentation due to the involvement of several engineering themes. Dr. Dodds has recently taken up the position as TWI's Nuclear and Defence Sector Group Manager and an active participant in a number of nuclear communities and working groups, which includes being one of our community of practice members supporting the RSO's advanced manufacturing theme and the newly formed ASME BPVC Section 3 Division 4 community looking at compliance associated with fusion energy devices. Dr. Dodds has a PhD from Sheffield Hallam University and previously researched the use of solid-state joining processes for the auto, defence and space sectors. Steve, welcome. Over to you.
Many thanks, Steve. Thanks for the opportunity to speak today. We've collected over the years quite a bit of understanding about how nuclear waste canisters might be made. And we've seen some commitment on those technologies and approaches that we've used over the years. And we'd just like to share some experiences that we've had in that topic. So in doing so, I've invited over a number of colleagues, or actually more precisely, I've invited the input from a number of colleagues and then trimmed down who might present, because I realised it was quite a glut of speakers to try and get through in 40 minutes. Please bear with us. So myself, Steve Dodds, previous life at TWI was friction stir welding, so I'm going to talk to you about friction stir welding of canisters. I was also provided information by Tim Mitchell, which is meant to say electron beam lead there, but it says B. Charles Schneider will be presenting. Now, Charles has started his career in the power industry, working mainly on the development of mathematical models for ultrasonic inspection. And then since joining TWI in about '97, he's continued to develop statistical models for the reliability of non-destructive testing methods. He's led independent qualification bodies overseeing various types of inspection, including ultrasonic phase array testing procedures for the nuclear sector. Then we're going to move on to Michael Roy. So he's our FEA lead, but also Michael might read us through the rest of the presentation if Yinjin can't make it back from a personal appointment. So just to introduce both, Dr. Michael Roy has a PhD in civil engineering. He joined TWI following 7 years as a structural analysis engineer in the oil and gas industry. And he has 10 years of experience under his belt for naval structures research. He is experienced in using sophisticated finite element analysis to validate, support and verify the design of components based on fracture mechanic principles. And Yinjin, if she can make it, has been employed at TWI since 2012. Yinjin's highly experienced in structural integrity engineering with thorough knowledge and experience of defect assessment, mechanical testing, technical peer review and design by analysis. Yinjin's a member of BS 7910 main committee, and along with other UK colleagues, She represents BSI on the ISO Fracture Toughness Testing Committee and is a UK delegate for IIW Commission 10. Yinjin has an NGD in nuclear engineering. So I'm conscious of time, so I'll crack straight on. Bear with. Okay, I think we all know why we're here. The idea is to store or to secure waste into the ground in a bury and forget sort of style. And in order to do that, we have to make sure that we cater for the remaining life of what the high level waste will produce. Therefore, if we are going to put them in canisters, whatever design they wish, the canister integrity is vital. And when we say vital, we mean it has to be leak proof and impervious. For 100,000 years is the sort of duration that we've been working on. So you'll see the flags at the bottom. These are all the projects that TWI have been involved in, and since I started at TWI in this new role as nuclear sector manager, it's really helped me pull all this together and see exactly just how broad and extensive our experience and knowledge is in this topic. TWI are typically quite humble, but I dare say this is a world leading expertise because we have worked very closely with all these countries. And the areas we've been working closely with, if I could give them a broad summary, would be canister design, the welding processes, and this is for steels and copper, the inspection procedures, but then also the breach and damage assessment models for that 100,000 year assurance. Now, the information I'm going to be telling you today is all public domain. It's a very good community in terms of sharing information. But the reason I'm also making a note of that is that we've got permission to share this from NAGRA and from SKB. The others we haven't approached to ask, so we won't be talking about any detail of them. I'll share these slides afterwards. There's some links there for all of the downloads that are available from both of these entities. And we're very, very proud to be involved in such depth with these projects. Okay, moving straight onto the technical. So friction stir welding of copper canisters. I have pressed next slide and I'm waiting for the videos to load because this is by far the most data hungry slide on the presentation. So whilst it's loading, friction stir welding is a solid state joining process where we're literally plunging a tool into material, creating a viscoplastic hurricane of plasticized material and stirring the joints together in a solid state manner. The central picture offers you the most detail for a simple joint, but the other ones around the screen show a variety of circumferential welds and also a bobbin weld, which nips from both sides and you can weld without having to use a backing plate or resistance from the face. The most interesting one for this meeting is the top right, and what you're seeing there is a friction stir welding tool spinning around, or should I say the canister is spinning around against the head of the friction stir weld. And that is a very typical finish of a friction stir weld. We want to see a little bit of flash expulsion because it means we've got high weld pressure. We want to see consistent weld tool witness mark at the end, following the tool, and we want to see that tool has got a nice glow which isn't pulsing around, and you know, the thermal management of that system is going well. Now, the reason friction stir is useful is because it is solid state, so you don't have any welding gravity effects if you were to go molten for a start. It's very simple preparation. We can work with any straight edge joint. There's no filler involved. Because we're not melting, there's much less heat energy going in, so we're reducing distortion and residual stress. Fully automated, these are all CNC G-code machines. Nothing, you know, there's no reason why you can't put a machining head in here as well and trim off the faces. And really useful for this sector, the QA is data logged, or sorry, should I say the data is logged for QA, so we can tell exactly what happened in a weld and keep a full weld history. Okay, so the challenges of welding copper, not just friction stir welding, but the main challenges are its high thermal conductivity. We're mostly working here with pure copper alloys. So we can see that the diagrams and the data there telling us what we already know. Copper is highly conductive, and what we don't need for friction stir generally in terms of weld quality is a shield. So we don't use a gas shield. We can, we've got tools developed for this already, specifically a material called Densimet, although other tools are available. And the conventional tool designs were okay with a little bit of a tweak. But your main enemy here is obviously the conductive nature. So just a few images of some of the development that we've done, and this is over since 1993, I think we've been doing this. And there's a typical weld log as well, showing you the temperature, the torque. And at the bottom there is a demonstrator cap that we've placed on, and you'll see that the tool, when you leave the region, leaves a depression with the displacement volume where the tool is. So the most effective way of dealing with this on this particular application is to park it away from the joint line. Other circumferential welds either pull the probe out gently to blend it in or drive it on to a wedge, which is later removed. The SKB project is by far the most extensive that we've been involved with from scratch, and that started in 1997 on flat plate. Then the circumferential trials at TWI for 4 years, and we had a secondment as well over to Sweden. Then we helped them design, spec and buy a machine over there, and then they went on to sort of production series just to prove off the technology. And then only after all of that investment and effort did they officially choose friction stir welding as their canister manufacturing technique. So that's a long time ago, 2005, but they've been busy doing lots of other stuff now that this has been nailed down, and they're only just starting to come back to it now to get ready for actually making these things in anger. It's worth saying that SKB have also developed some interesting technology, which is to do with the temperature probing of the tool, which is really your only useful contact point to tell you what's happening at the weld. And then we're able then to modify, using that and a combination of the machine torque, we're able to modify the parameters on the fly to maintain a steady temperature. The other thing that SKB found out is they wanted to use an argon shield, not because of the weld, but to protect the tool from oxidation when it was removed. That's a very quick whistle-stop tour of friction stir welding. Another technique that we could use here, either for the copper or for the steel elements of the canister, is electron beam welding. So electron beam welding, as some of you may know, is a autogenous welding technique with very precise and high quality beam. And the surface finish in general is excellent. In fact, it's often used to redress joints. And it can go very thick penetration. However, standard EB welding can often leave to quite a sharp root tip at the very bottom of the weld, which isn't great for the sort of the modeling that we were looking for and the microstructural abruptness, the changes in microstructural texture that we were getting. So TWI helped develop a reduced pressure electron beam, and instead of 10 to the -4, 10 to the -6 vacuums, this is to the 0.2 millibar vacuum. What we've effectively got here is a much more production friendly system, which allows for significantly less vacuum downtime or even local vacuum around the canister head. Also, it allows for a slightly broader beam, which can also be wobbled around. Sorry for the untechnical phrase, but that means we're able to round out the root of the electron beam weld to offer a more gradual change in microstructure around that point region. There's other benefits as well mentioned at the bottom, but this was specifically targeted as a technology for canister design because of the production environment, because of the weld requirements, and because of the scale of the objects that we were welding. And here's some images of TWI starting to play with some really big stuff in the electron beam chamber. I don't know if you can see my mouse, but this is where the electron beam is emitted, and you roll the part around, and then that was then transferred over to SKB as a reduced pressure system specifically built for their trials. Here's a section of copper canister. So you can see here a 15mm penetration, partial penetration, and that was then used for the corrosion testing that we did as well. And then finally, some big pictures again of the copper canisters, either seam welding the bent copper plates together to make tubes, or on the top there, this is a castellet sort of tooling system where we first tack weld in between the braces and then take off the tooling system and go for the full circumferential weld in one go. So that's a very whistle-stop tour of the manufacturing technologies. Please come and have a chat with us if you want to know more. There's also quite a lot on the internet as well available. I'll hand over now to Charles Schneider. Thank you, Charles.
Thank you, Steve. I hope you can all hear me. You've had a bit of background to me. What I'll add is I tend to be the first port of call at TWI for non-destructive testing input to structural assessment, particularly. So I work closely with our colleagues in that area, generally using BS 7910 for assessment of welds. What I'll do in this talk is give a flavour of how we determine or have determined NDE requirements for canister projects and how NDE issues impact on canister design. Again, I'm conscious of time here, so there is actually more information in these slides than I'll actually describe in detail. Could we go back to the previous slide? I'm not actually in control of this. Thank you. So first of all, what we do is to agree floor descriptions with welding engineers and material specialists, and our approach is to split this into what we call high priority floors, for which you'll typically need inspection qualification, lower priority floors, nice to have, and floors that can be excluded from further consideration because of the control of the process. And then we provide some indicative detection capabilities for those floors, and I'll give you some examples of information that we've produced for a canister project. And we'll consider the effects of the proposed weld design on inspectability and suggest changes where that's possible. And I'll give a couple of examples to do with unfused land and access. So high priority floors, by definition, need to be reliably detected, considered for inspection qualification, and they typically might be of structural concern, typically more than 3 millimeters high, but obviously that depends on the design. And we'll list those for each of the candidate processes, 2 processes here of narrow gap TIG and electron beam that Steve was talking about. I won't go through the various floors, but this gives you an example of the first step in the process and some pictures here of typical floors for those 2 processes. Next slide, please. Low priority floors. Here, detection is desirable but not essential. So that means they are considered when designing the inspection. They are considered when coming up with reporting criteria, evaluation criteria, but for instance, they may be volumetric, so they're not of immediate structural concern, so they're not necessarily included in the inspection qualification process. Typical floor descriptions for this are volumetric inclusions. We expect them to be easily detected, but they're unlikely to be large enough to be a structural concern. Or wormholes, again, we know they'll be readily detected because they're similar response to calibration reflector. Or porosity, if they're gross enough to be of structural concern, they're very likely to be detected by UT. Okay, next slide, please. So I'm not going to go through this, but here's a case where we were considering conventional UT of ferritic welds, and we've drawn out various literature, a lot of which is included in BS 7910, and this we look at in relation to the floor types, particularly where qualification or high reliability of detection will be needed, and we identify any gaps or issues. Next slide. And we can do a similar thing for advanced UT methods such as focused phased array. And if you were to compare this slide with the previous one, not surprisingly, you see that there are smaller flaws detected, and so a comparison of the two can be done during structural assessment to work out the implications of that for potential canister breach later on in life. The idea of all this is to have a damage tolerant approach. Next slide. And here we have eddy current or eddy current arrays for surface floors, and one of the things that you find here is that you've got quite a small floor size of 1x5 if you have a machined or ground surface, whereas if it's an undressed weld cap, you probably have little advantage over ultrasonic testing. So that all feeds into the choice of preparation of the surfaces and choice of techniques. Next slide. Another thing that we found has a potential effect on inspectability in the design is unfused land in a partial penetration weld. And one of the early designs we had, there was unfused land that was a continuation of the weld centre line. And that means it's more difficult for the NDT to distinguish unfused land from extension of the unfused land. And that means greater operator skill is required, increased time and cost for data analysis, and less accuracy because it becomes a sizing exercise rather than a detection exercise. And there are ways of getting around that by changing the orientation of the unfused land. So that provides a useful input into inspection, the canister design. And similarly for access, a lot of these canisters need lifting features for handling, but the positioning of those potentially affects the capacity of the ultrasonics to achieve high enough beam angles onto the weld centre line. So by just some fairly cautious repositioning of features, it becomes possible to get a better inspection moving forward. Next slide, please. So I'll now hand over to the people who take all of that input and use it to work out whether indeed the canister can tolerate the flaws that might potentially escape inspection. Thank you.
Thank you, Charles. So Yinjin, I'm glad you can join us, and Michael's also presenting, I think, the front end of this. You guys have got 20 minutes. Thank you.
Okay, yeah, thanks, Steve, and thanks, Charles. So I have to leave in 10 minutes, so anything after that, Michael will continue.
Thank you.
All right.
Cheers.
Okay, so so within this tens of minutes, we're just going to go through what we have done to support the Swiss nuclear waste management project program. So we're looking at three main topics here: the background, where to get to where we are today, what's driving it, and then the design optimization using both fracture mechanics and ECS, and also the third element in this is the probabilistic approach to determine the distribution of breaching times of a nuclear waste canister. So this is the Swiss geological disposal repository. So so they're going to dig, go underground, and then with the canister buried beneath that piece of land, and then the idea is to have the license application approved, submitted, and approved by the end of the next year. And obviously the main concern here is to demonstrate that we have looked at all the options in terms of designing a container to store the nuclear waste, and also look at the different concepts, and also look at how the storage condition would affect the longevity of these canisters. Next slide, please. So we did this program here examine how the materials will perform for at least 1,000 years. But usually when we're talking about analysis, we're looking at long-term stresses. And because the way the canister has been designed, so basically we have a cylinder, and then you load the nuclear waste on it, and then you put a lid on, and it's the closure lid that is the most critical part of the whole cylinder. And so with this, we bring together the friction mechanics principles and FEA and some support from the geologist from Switzerland to see to understand the conditions that this nuclear waste will face in the next hundreds and thousands of years. Next slide, please. So one of the way to optimize the design is using what we call deterministic approach. So by deterministic, I mean we are working with a set of known parameters or parameters estimated from models, and then with that we determine try to establish, are we using the right welding process for the closure well? Is EB more suitable than a friction stir welding, for example, or could we go with a narrow gap arc welding? And then this then also would affect the inspection method that the authority is going to use to determine the possible cracks that will be present in the closure well, and also considering the long-term performance of this canister. There will be one institute that will prefer copper material, for example, but no others will prefer stainless steel, and there were some that will prefer carbon steel. And all this, the performance of all this material in the long run during the storage period has to be understood. And then part of this exercise, we also look at how we can optimize the dimension and the shape of the canister, especially how the closure lid could be designed to minimize first minimize the occurrence of defects, and to facilitate the closure well application, and also looking at how we can control the material composition, the material properties, so that it gives us the performance that we want in the long run. So in all this analysis, we then take into the friction mechanics calculations, and then to determine which of these bits is the most significant factor. Next slide, please. So in all the work that we've delivered to support the NAGRA program, we have employed the defect acceptance procedure described in BS 910. So this is our BSI procedure. And then this procedure alone is not sufficient. So we've called on more sophisticated FEA analysis to look at the loading conditions, material response during both short-term and long-term storage periods. And then in our work here, we have for the closure well, we have decided that EB welding process will be the most appropriate. Not just because of the marvelous production rate, the overturn of the canister, but also it can be easily automated. And with this, then we look at what sort of parameters we need to achieve a sound weld, and then these parameters are then fed into the welding simulation, which Michael is going to explain a bit later. And then with those simulation, we predict the residual stress, and then what happens if we apply post-fight treatment. And then all this then fit into to determine the acceptance criteria in terms of flow sizes for these canisters. And where possible, we propose, if you have the material and the funding, then do some testing to give you confidence of the material properties. Next slide, please. So this is just a very generic graphical presentation of how we use a deterministic assessment. So basically, we have you see the diagram in front of you, where this diagram is been established using friction mechanics principle. And then within this diagram, we have a region of acceptable area and region of unacceptable area. So basically, all the calculation we did is just to determine the assessment point, and then from the assessment point, we then can conclude how the material would perform under a given set of conditions. So this is what we typically refer to a failure assessment diagram. Next slide, please. So from this point onwards, I've passed over to Michael because he's our FEA expert, and I don't know what I'm talking about in terms of FEA. Over to you, Michael.
Thanks, Yinjin.
Yeah, thanks, Yinjin. You're not doing yourself justice there. But yes, this slide is showing some of the finite element analysis that we've been doing to support the assessments that Yinjin has been talking about. Steve, if you want to click on the animations, I think they'll start working. But so the first one there is showing a simulation of an electron beam weld. We can use that to predict the residual stresses that we get as a result of making that closure weld. And then over to the right, if you can see my mouse pointer here, we do a post-weld heat treatment process. So we can simulate that post-weld heat treatment process, how the residual stresses reduce during that. This particular one is induction heating, electromagnetic induction. The next thing, another potential source of stresses in the closure weld, is transport. What happens if there's a handling incident while the canister is being transported to the repository? And that's what you're seeing here. Canister potentially falling off its transport bed, a dynamic incident. And so we can calculate those dynamic stresses that would be applied to any potential defect in the closure weld, and we can feed that into the assessment. And then finally, down at the bottom, the canister's in the repository. It's experiencing all the loads that come from the rock around it, the geological loads, lithostatic pressures, and what kind of stresses do they generate? Again, finite element analysis to compute those, looking particularly at what's happening around the closure weld. So we've had, over the various projects that we've done with NAGRA, we've looked at developing these, and we've also looked potentially at doing testing to establish those. All of that is the deterministic approach to how we can calculate, for the purposes of design, how we can calculate and evaluate and assess the structural integrity of the canister, and how we can demonstrate, using conservative assessments and conservative inputs, how we can that it's safe for the duration that's required. But actually, we know that some of those, and everyone here knows that some of those parameters are uncertain. We don't necessarily know. We can make a conservative assumption, but we don't know what the right value is. And some of them are variable inherently. For example, the distribution of defects is variable. And some of them evolve over time. So Steve, if you want to go to the next slide, please. In parallel to what we've just talked about, we've also been developing a probabilistic model to evaluate, based on these uncertainties, what is the probability that the canister will be safe for a particular time, taking account of the variability in the inputs. These from now on, these are my colleague Juan's slides. This is her work. But you can see the model accounts for variations in temperature and humidity, in lithostatic pressure, and how that evaluates over time, as the clay swells, for example. The development of corrosion over time and its potential reduction in wall thickness, hydrogen ingress, does that affect the material properties? The variation of potential defects within the weld. This refers back to what Charles was talking about earlier. And as we all know, material properties can vary. So what is the effect of those? Next slide, please. Based on all of that, we can put all that together, and we've developed this probabilistic model. The terminology here, a realization, is a calculation for one set of input parameters evaluated over time to give a prediction for how long, based on that set of parameters, how long it would be before the canister could no longer be considered to have acceptable structural integrity. and the program will sample all the distributions of possible inputs. You can see them listed there. It then runs the calculations that you can see on the right, which account for hydrogen ingress, structural stresses, defect positions, corrosion, and makes a calculation of the structural integrity based on that for the particular set of inputs that it's sampled. If we move to the next slide, it's a bit easier to see, please. I like this illustration. 3 colours. Going back to the failure assessment diagram that Yin-Jin explained earlier, but the 3 colours represent 3 different realizations, so 3 different cases. The black one, the blue one, and the yellow one. In each case, we've sampled from the distributions of inputs a particular set of parameters. We've calculated where it is on the failure assessment diagram. It's okay at the start. That's the first point. And then as time evolves, we recalculate the loads. How is the corrosion reducing the wall thickness? How is hydrogen ingressing into the structure and degrading the material properties? How are the loads evolving over time? And that creates a series of further points until eventually we get to the point where we can say we're now outside the failure assessment. The canister can no longer be said to have acceptable structural integrity. And we note the number of years, hundreds of years, thousands of years it's taken to get to that, and that gives the breach time. So this here is illustrating three realizations, 3 sets of sampled inputs, and they would give 3 different breaching times. Okay, but now if we move to the next slide, what happens if we run that a large number of times, say 1 million times, for the sake of argument? We sample the inputs 1 million times, we run the calculation 1 million times, and we generate 1 million breach times. And that gives us a distribution based on the distributions of the inputs. That gives us a distribution of the possible breach times. You can see that the top graph is showing, this is obviously example output, it's idealized, there's no numbers here, but we might get, for example, a distribution of probability of occurrence of a particular breach time for spent fuel canisters, and we might get a different value or different distribution for high-level waste canisters. The bottom slide is showing the same thing, but presented in terms of cumulative probability. So that's now looking at what is the probability that the canister will have a certain number of years, 1,000, 10,000, 100,000, whatever. What's the probability that it will have that number of years before it has no longer has acceptable integrity? So NAGRA can use that information as part of their safety case. They can use it for what if scenarios. What happens if we vary these distributions of inputs? What happens if we control this one better, or we find a bit more information about that? How would that affect our knowledge of the likely acceptable life of the canister? So for both of those, that's the probabilistic assessment. Earlier we had the deterministic assessment that we can use for design. And we've been putting both of those together with the welding technology that you saw earlier, with the NDT that you presented earlier. We can put all of that together to build a safety case for the integrity of the canister for a particular design. That brings me to the last slide and the end of the presentation. So I think I'll hand back to Steve at this point. Thank you.
Many thanks to Michael, Yin-Jin and Charles. Astoundingly, we have 3 minutes left on my clock, which went better than planned. And thanks, Steve, for the opportunity to present this. We went for breadth rather than depth. I hope everybody didn't mind the skipping over of stuff that's quite interesting, but we're always receptive to your phone calls and emails to talk about it.
Thank you very much, Steve, and thank you to TWI colleagues Charles, Schneider, Yin-Jin and Michael there, Michael Roy. You're absolutely right, Steve. It's such a wide subject matter, bringing in and incorporating many technologies. And I would encourage those who have got an interest in those particular themes that have been discussed by TWI to contact TWI, or even come to our community of practice meetings. And this is where some of this material will be discussed further. And So once again, my sincere appreciation from the NWS RSO's Advanced Manufacturing team for the support that Steve has put together here. And that leads us very nicely into our comfort break. I'm conscious that we are 4 minutes early, which is absolutely fantastic. So thanks once again, Steve, for doing that. If we could break for the comfort break now for, let's say, 5-6 minutes and be ready to go again at just 1 minute past 10 to 2, that gives Arij and Matthew some additional time and also pick up those questions at the end. So Sam, if we could pause recording for 5 minutes, that would be fantastic.
Right, welcome back. I'm very pleased to introduce Arij Asad from the University of Bristol to present on a research on ventilation of hydrogen in disposal vaults. Arij is just starting her second year of a PhD, having graduated with a BA in mathematics from the University of Cambridge in 2022. Over to you, Arij.
Hello, yeah, I'm just sharing my presentation. Hopefully it's okay. Can everyone see that? Okay,
Yeah,
I'll
fine.
start now. Okay, good. Hello, my name is Arij Asad, and I'm currently working on a project looking at the ventilation of hydrogen in unshielded intermediate level waste vaults, and I'm being supervised by Dr. Andrew Lowry and Dr. Stuart Thompson at the University of Bristol. So the part of this project that concerns me is the gases that are released from nuclear waste by radiation hydrolysis. The waste produces hydrogen gas, which poses a significant safety risk, as for concentrations as low as 4% to 75%, hydrogen becomes combustible, and even explosives in the range 18 to 59%. So the key scientific challenge consists of estimating the rate of molecular mixing of the hydrogen released with ambient air, because over time the mixture may become density stratified, providing a potentially flammable fuel-air mixture at some height within the vault. So an important step towards addressing this risk is to make validated predictions of how a less dense fluid discharge into a more dense fluid modifies the conditions within the vault. So in a series of experiments, which I'll present in this talk, the density is controlled by salt as a solute in water, and this approach enables a scale representation of the buoyancy of hydrogen gas discharging from nuclear waste packages into air. So I'll look at two cases, the case where there's no ventilating cross-flow and the case where there is a ventilating cross-flow. I'll also present an analytical model for the case where there's no ventilating cross-flow, and also I'll present just the results from my experiments for all the cases. So just a quick overview of the experimental setup. So the experimental setup consists of a rectangular tank of dimensions 800 by 400 by 450 millimeters, with a video camera that's recording the flow as it comes out of an orifice that's contained within a smaller pipe within the tank. I'll show an image of the setup on the next slide, but just a quick overview. So there's a header tank. Actually, I'll pull up the diagram now. I think it'd be better to explain while it's showing. So yeah, so within the tank, I have a header tank over here, which contains fresh water, which is dyed with rhodamine 6G. Also have a laser with maximum power of 30 milliwatts. In this case, that's protected by a laser guard, just for safety reasons. I'll have a supply that's coming from this header tank, which contains the rhodamine 6G, coming in through this orifice supply into the orifice over here. So the whole thing is illuminated by this laser that works well with the rhodamine dye. I'll also have a smooth intake profile over here, which helps the streamlines converge as they come into this working section. So essentially this pond pump on the end creates the circulation within the tank, which will create sort of this cross flow coming through here. So basically it's a prototype of the GDF the facility. And yeah, this orifice over here, that can be sort of changed. So I've used a range of orifice sizes, which were quite easily fabricated using a 3D printer. And the achieved changes in pressure gradient allow the injection rate to be varied. yeah, so essentially this is the setup that's used to investigate when there is a ventilating crossflow, and then I have an almost identical setup on the next slide for when there's no ventilating crossflow, and the only difference is there's fixed caps on the end in this case where there's no ventilating crossflow. So just for the first set of results, so for the open ends without a crossflow, I have my results here on the left hand side. So each column represents a different orifice size. So we have 2 millimeters in the first column, 3 millimeter orifice size in the middle column, and 4 millimeter diameter in the right column. So there's like a hole of that diameter for each column, and time sort of moves on as we go down the rows. And we can see that there's very clear sort of destabilization as we get to about here. Just before the experiment runs out, there's entraining fluid. There's fluid being entrained very clearly over here, because we can see that there's so the black represents the salt water and the green represents the dyed fresh water. So we can see that we have sort of this salt water coming into this the plume of the fresh water. So we can see clear signs of entrainment and vorticity being dumped at the top. And then also just apologies for the messy graphs. It's just the way that it's been plotted with the program that I had. So I had so we can see that as time passes, that's demonstrated by the black arrow. We can see the stratification becomes sharper. The passage of time is measured by the colour saturation of the lines, where darker colours indicate later times. And we can see that d rho by dz, so the rate of change of density with respect to height, is maximal for the 4 millimeter case, as the dye layer thickness is greatest, since the flow rate is higher for the largest nozzle size. Yeah, and then similarly had the case where we just had a very slow crossflow speed going when the ends were open as well. So we had a 0.48 centimeters per second crossflow going through the working section. So the environment once again became more stratified to begin with, and then becomes less stratified with time. I think this can just be explained by the fact that less buoyant fluid is going to want to come out the sides of the pipes and just come out the working section. So the dye is obviously going to escape from both ends. We can also see the dumping of vorticity in this case as well. And so yeah, very similar conclusion in this case. And then I also have the density plotted against height for this case too. We can also see for this case, as time passes, as sharper stratification also develops, we can see that d rho by dz is maximal for the 4 millimeter case as well here. Same thing, and yeah, and there is an anomaly in the data for this case. We're hoping once we do some repeats and rerun these experiments, that won't happen again. Still unsure as to what was the cause of that. But yes, and then now maybe the case that I looked at more closely was the sealed working section, where we had those fixed ends on the fixed end caps on the working section. So the environment does become more stratified with time in this case, and we can also see clearly from the data that there's a regime of undyed fluid being entrained alongside the plume by induced velocity. It can be seen that the amount of dye collected near the top of the working section also increases with time. And I've also done a plot for this one as well, where we can see how density varies with height. So the passage of time once again is measured by colour saturation, and just the same sort of presentation as before. And we can see that as time passes, d rho by dz becomes greater for different heights in the working section. Yeah, and so for this case, I did investigate, sort of look into coming up with an analytical model for it. So we can see that the stratification that evolves with time in the closed case is the most marginal for explosion risk because of the buildup of hydrogen. Therefore, I'm going to present an analytical model using a diffusion equation with a moving boundary. So we can see, so phi in this case is a scaled version of the density. The reason I've done that is just to make it a bit easier to solve. So these are the boundary conditions. At time equals 0, obviously the moving boundary is at the top of the tank, it hasn't quite moved down yet, so that's going to be 0 at the start of the experiment. Phi of 0t basically is what's the value of phi at the top, and that would probably be the same as freshwater. And then along the moving boundary, it will probably be the density of salt water just underneath. So that's how I've scaled it. So when you solve these equations, I get this solution for phi, and then I've scaled this back up to get to the actual density values that we want, where 5s and 5f are densities of saltwater and freshwater respectively, and lambda appears up here, where it's just a constant that I've used just to make the equation look a bit nicer. So this is what I plot. However, I don't have a value for kappa, so I've made a few mathematical assumptions and come up with something for that. So by using Prandtl's mixing length hypothesis, where kappa is equal to gamma times u times L, where u is the velocity scale and L is the length scale. So by taking the velocity scale to be given by a dynamics balance between buoyancy and inertia, I come out with this equation, which I just simply rearrange for kappa by making a few more assumptions. And then by taking this value for kappa, I then plug it into the equation in the previous slide for lambda, and I can basically come up with a scaling for how the height varies with time, which is t to the 2/5. So just to test some of these equations that I've come up with, I did do some plots and compare them to the experimental results. So what I have is a plot of density against height for a 3mm nozzle as time evolves. We can see that the smooth curves are the analytical solution and the more jaggedy lines are the experimental results. And we can see that we have quite good agreement for the two. For this case, gamma is equal to 0.023 for a 3mm nozzle. So I thought that was quite good agreement for this error function solution, and then did the same thing with the 4mm nozzle and also got some good agreement for gamma is equal to 0.0075. As well, we also tested I also tested the how the height varies with time, so where h was this sort of moving boundary height. So we have the smooth curve is the analytical solution, and then the dotted lines are the experimental results, and we can see we have some good agreement. Towards the end, the experimental results do seem to plateau, but this can probably be put down to the fact that the header tank ran out of fluid. But yeah, so got some good agreement there. And then also, I also ran a case for when I had a row of plumes. So I had this little nozzle that had a few holes in it. We can see the dye does not collect as strongly at the top of the working section for the case where the ends are open for similar reasons. So this is the open case, probably because the dye escapes from both sides, and then the closed case, it just is left to build up. We can see that there's more instability at the ends of the array than in the middle. I think this can also be explained by the fact that the supply is connected to the center of the row, so most of the force is probably coming into the middle. But yeah, I think the important observation to take from this is that there's little net vorticity with multiple plumes. So the mixing rate per unit of injected volume is lower, and therefore the flammability is reduced. So there's less vorticity in these cases from when there was a single plume, which is quite interesting. And I think it says something about flammability of the hydrogen that builds up. We can also see evidence of necking. But yeah, that was quite an interesting case, which I'm going to look at in more detail, hopefully soon. But yeah, so obviously there's always room for improvement. The next steps would be to improve the quality of results. So to get a more powerful programmable laser and program this, coordinate this laser with the camera, so the laser pulses while the camera's triggered, so we can deliver more power from the laser, because having the laser pulse is deliver more power than just having it continuously switched on, like I've had in this set of experiments. So this will probably result in greater contrast between dye and water, which will give better images. And then future work, there's also a lot of things to be said there. So for the study of the interaction of multiple plumes, the header tank volume was far too low, like it needs to be greater because the flow rate being used was too high and the experiment ran out quite quickly. We can model the closed-end experiments by, rather than using this small working section in the tank, probably use the entire tank instead, which would also be easier to model because modeling a circular pipe is more difficult than a sort of a cuboid shape, easy to solve differential equations. And since in the end application, the leakage of hydrogen would most likely occur over long time scales, it'd probably be useful to have much longer timescale experiments. So the experiments I ran for this set probably ran out in 25 to 30 minutes, which is nowhere near how long we're expecting this leakage of hydrogen to occur over. So we'll probably take advantage of the programmability of the laser and camera and just make some automated measurements rather than having me sat in the lab the whole time watching what's going on. And thank you for listening. I'll leave you to read the conclusions yourself, but yeah, thank you very much.
Thank you, Arij. The passion and the speed at which you know your subject is quite phenomenal, and we need more people like yourself to take up that challenge. So thank you very much. I'm sure we'll have some questions. I certainly can see a benefit of this capability within my particular area, but there's so many opportunities elsewhere that you're working on. So thank you. I'm conscious of time, so I'm going to take the advantage now of introducing our final speaker today, which is Matthew Riding. Matthew is a third-year PhD student within the Future Innovation in Non-Destructive Evaluation Centre for doctoral training based at the University of Strathclyde. His research project is focused on developing new ultrasonic inspection techniques for use in challenging environments, such as those encountered in nuclear fission and fusion power plants, where some of his work is also in collaboration with the United Kingdom Atomic Energy Authority. So Matthew, very interesting when I saw you up in Strathclyde early in the year, and really pleased that you've taken the time to come and talk to us about this. So Matthew, over to you.
Thank you very much, Steve. Yes, thank you very much for inviting me to talk here today. Just start sharing my screen. Okay, I hope everyone can see that just fine. If there's any issues, just let me know. I will start. So yes, thanks again for inviting me to talk here today. I've really enjoyed the other presentations so far. I'll be talking about laser ultrasonic inspection for nuclear applications. And I'll give thanks up in advance to all of my colleagues from my laboratory for their support in this work. Yep. So to give you a bit of an overview of the presentation today, I first just want to anchor this in something that everyone will hopefully be familiar with regard to ultrasonic inspection. I'll give the classic example from medicine. I then want to introduce the idea that ultrasonic inspection is also widely used in industry and to evaluate the health of engineering structures, and that this is mostly done using piezoelectric transducers, which are also very familiar from the medical field, which couple to samples with a sticky gel. I'd then like to introduce laser-induced ultrasonic inspection as an alternative form of ultrasound transduction, and show how it is potentially more widely applicable in challenging environments when compared against the piezoelectric transducers. The laser scanning assembly that we have at the University of Strathclyde and which I work on, and then I'll present some case studies of work that we've done with relevance to nuclear applications. So using ultrasound is all about seeing inside things, and seeing inside things without having to invasively cut them open to see the features that are invisible from the exterior. And so the classic example is in obstetrics for antenatal screening. It's a non-invasive technique, and it's also non-ionizing, and that's why it's really widely used in medicine, especially at these sensitive applications, and it's really useful there. I'll point out couplant at this stage. This is going to be a bit of a theme of my talk, sticky gel that's needed to couple these traditional piezoelectric probes onto their targets for contact-based ultrasonic inspection. So for the same reasons, ultrasound is very useful in industrial applications for examining structures, engineering structures, solid structures, for defects. You can see in this animation a probe being used to detect the presence of a otherwise invisible reflector buried within a block of metal. And the echo from that reflection is appearing on a sort of graph readout of time of flight of the ultrasonic waves. In some more advanced applications, ultrasound can be used for imaging, and so we have imaging algorithms that we can use to process ultrasonic time of flight data into spatial images. Couplant, again, ubiquitous in all of these pictures, so it's being used to couple piezoelectric probes to their targets. So nuclear applications have some really challenging requirements. One that I'm particularly passionate about and that I've been exploring in my work is application to nuclear fusion. This is a fusion reactor, a future fusion reactor, presents a radioactive environment, an ultra-high vacuum environment, depending on the specific components that are under inspection, and other really exotic parameters such as high magnetic fields. And these make it challenging to deploy many existing non-destructive evaluation methods for the inspection of these types of reactors, including piezoelectric ultrasonic transducers. They will not be welcome inside the ultra-high vacuum environment of a tokamak. As a hopefully more relevant example to the theme of today, this diagram I've taken from a publication on waste immobilization and the manufacturing processes that go into that. And again, we're seeing radioactivity, elevated temperatures in this application, the desire in general not to come into physical contact with the inspection targets, and also maybe a vacuum. We've heard presentations about electron beam welding today, which is a vacuum manufacturing technique. And so an in parallel in-process inspection would have to be compatible with that. And so again, we're seeing examples where these gel-covered piezoelectric transducers are not going to be welcome. So this brings me on to introducing the idea of laser ultrasonic inspection. When you use laser ultrasound, you can induce an ultrasonic pulse through a short pulsed laser that rapidly heats the surface of a sample. The rapid heating generates rapid expansion of the near surface material, and that expansion is accompanied by the emission of acoustic waves downwards into the bulk of the sample. These propagate and reflect off acoustic discontinuities such as cracks. We can then use a second laser system to detect the arrival of those echoes back up to the surface of the sample. This will output a plot of surface displacement over time, also known as an ultrasonic A-scan, and collects data that looks very similar to the piezoelectric transducers. So by this means, we have now an all-optical, non-contact ultrasonic transduction technique. University of Strathclyde, we've implemented this with a twin laser scanning assembly. I have a little video here that shows the lasers being manipulated on the surface of the sample. You can see a camera view of the surface of the sample on the right and a camera view of the laser delivery heads on the left. We can manipulate both the detection laser, which is green, and the generation laser, which is shown here in red, in both X and Y. So this brings me on to the idea of phased array imaging using laser-induced ultrasound. Using our assembly, we can position and scan our lasers over the surface of a sample and capture A-scans in a process known as full matrix capture. This is to synthesize a phased array in post-processing. We apply a standard ultrasonic imaging algorithm known as the total focusing method, and that allows us to generate ultrasonic images of the subsurface reflectors inside our samples. Non-contact, non-destructive ultrasonic transduction scheme. It requires no couplant, it's just shining the lasers onto the surface of the sample. Let's point out in this case that the array is much smaller than the imaging domain, so we can take advantage of the outward propagation of ultrasonic waves to image a wide domain from a small array aperture. So now moving on to some case studies that I've personally worked on. These are the samples that have been sent to us by our collaborators at the UK Atomic Energy Authority. They sent us, they were interested in inspecting welds for tokamak power plants, especially in low contamination areas of the power plants, such as from the interior of pipes. So they sent us this TIG welded plate just to get us started and see what we could do with it. And then more recently, they sent us a laser welded pipe. And both of these samples contain defects. The plate has an artificial defect in the root of the weld, and the pipe contains a naturally formed sort of keyhole type defect at the end of the laser welding process. So we went hunting for those defects and tried to demonstrate a detection of both in these samples. So here's the plate mounted in our laboratory with the lasers illuminated on the surface. It's a stainless steel plate, austenitic. We formed a phased array to the left side of the uneven cap. We're working on going straight onto the cap, because that's something that the lasers can do potentially better than the transducers. But for now, just to make a nice comparison against the transducers, we're doing a phased array to the side of the cap. So looking at a cross section, we build an aperture up to one side of the cap, and then we're targeting the root defect, which is down there out of aperture at 12 millimeters depth, and with the following small dimensions. Those are the scan parameters. The limitation of the technique at the moment is the time that it takes to capture the signals, but we know that there are built-in bottlenecks in our setup. It's not currently been optimized for speed, and so that's the major priority of our ongoing work. So here are some TFM images, and we're able to see the defect very clearly, which is a really exciting result for us. This, at the time, was one of the thickest samples we've examined in terms of the distance of the defect from the surface. So down at 12 millimeters depth, so it's a decently thick plate. We're able to see it with different views. So this is a self-tandem imaging mode, where we're able to see the defect at a nice upright orientation. And with different wave modes. Laser ultrasound is a highly multimodal ultrasonic source, and so we generate all of these images from the single data set, from a single scan. So you get lots of different views of the defect. It was good to see that when we moved further down the weld to a nominally defect-free area, those indications at the root of the weld all disappeared, and so that's nice evidence that we were genuinely detecting the presence of the defect. Moving on to the pipe now. This is a slightly different material, a martensitic sort of nuclear grade steel, 90 millimeter bore with a 5 mil wall thickness, significantly thinner than the plate. It had a flat prep laser weld inside it, with a width of about 2.5 millimeters on both the inside and outside. It was welded from the inside using a bespoke laser welding tool at the UKAEA. And the defect we went looking for was this keyhole defect that's visible from the inner surface, and came up as incomplete root penetration on this radiography report. So that would form something like this in the cross section of the weld, a sort of inward pore on the inner surface of the weld. In terms of scan strategy, at this time we actually captured a series of images. So we started at one position on the surface, the outside surface of the pipe, and then took a second array image at a next location, and then took a whole series of images over covering a 90-degree sector of the sample. Just to be clear on the laser configurations there, we've got the lasers coming in from the side stacked above each other, and then focusing on this 90-degree sector. And if we started at 0 and moved to 90, I manually positioned the defect, which I can see on the inner surface, at approximately 60 degrees into the scan, to give us something to look out for. We kept the lasers fixed, rotated the pipe on a rotation stand to complete the scan. There are the scan parameters, a much smaller aperture for this one, and each individual capture was quite quick, just less than 2 minutes, but the overall scan time for completing this 90-degree sector was almost 1 hour. So again, speed is a real drawback at this stage, but it's not been optimized for speed, so that's the priority of our future work. The video of the scan proceeding. This is using the alignment lasers that are eye safe. At full power, the video looks more like that, which is significantly less interesting in my opinion. And then I'll present the images to you. So we're forming an aperture to one side again of the weld cap on the outside. We're looking for a defect down at the weld root. So I'm going to present all of the images we've captured stacked into a 3D volume in the top left, and then it's going to step through each image individually, highlighting with the magenta plane, and it will display that corresponding image in the top right. The bottom plot is a slice through the 3D volume at the depth of the back wall. There's one outstanding indication, and I hope it will be clear to you when I play the animation. There we go. Is plotted in the title of the image in the top right. And we've got this very strong indication at the backwall depth for an angle in that scan going from 0 to 90 of 57 degrees, and I was aiming for 60, so I clearly have a 3-degree positioning error in my hands. But we're pretty pleased that we've been able to detect it and that it's so clear. The whole 3D volume is normalized to the amplitude of the defect, so it's really outstanding compared to the whole all the signals captured across the scan. There's a signal to noise ratio for the indication. And then we can likewise render multiple views using different wave modes, taking advantage of the highly multimodal nature of laser ultrasound. And again, we're seeing a very clear indication here of the defect at the same angle. So just to finish up, one final application that I mentioned earlier and which I've been pursuing in my work is the in situ inspection of plasma-facing components in tokamak reactors. Now, these are very high vacuum environments, and you don't want to start coming in here with a gel-coupled probe and smearing liquids all over the walls that'll take ages for them to decontaminate. So this is a potential environment where laser ultrasound could be very helpful. The idea would be to deploy the laser ultrasound inside the vacuum vessel via a robotic manipulator or maybe a wall-mounted system as well, and go and inspect the armored tiles that cover the inside of these reactors. The material that's really relevant to this is tungsten. This is the prime candidate material for future power plants, mostly selected for its high melting temperature and thermal properties and resistance to sputtering. And so I'm very pleased to have been able to demonstrate with the tungsten sample I borrowed that we were able to image the tips of these slots in this artificially defective tungsten sort of bar, which is really exciting. And we're continuing this work to look hopefully at further samples relevant to these components. So I'll leave it there. Thank you very much for your attention. And yes, it's been really exciting to present here today. Thanks.
Thank you, Matthew. Once again, like Arij, so passionate about your subject, and I've been very lucky to witness the activity firsthand whilst visiting you last February. I just want to sum up before we go to the question and answers session, but I just want to thank all our presenters, Steve Dodds, Charles Schneider, Yin Jin, Michael Roy, Arij Asad and Matthew Riding for giving us this fascinating presentation. And I'm sure all of those who are still with us can see the fact that there are opportunities from other sectors and there are opportunities that will be created by the GDS research programs into other sectors. So this is a win-win opportunity for all that are involved with this program. I can see the presentations are obviously going to be used for many forums in the future. And I think what we see here is the potential for the advanced manufacturing community to be inundated with a wealth of information that could possibly be used to explore future research themes in the future. I'll just see whether Richard would like to add any comments from his side before we go to the questions. Richard, would you like to say anything, or do you agree with
yes,
what
yes,
said?
please. I'd certainly agree with all you said, and just want to say thank you on behalf of Nuclear Waste Services, because those presentations were really excellent quality, and Very fascinating, very relevant to our research work. Should we go to the questions now?
Thank you. Yes, I've been making some notes of questions, and I typed some questions in myself because I'm really keen that the community and the people who've taken the time to join the webinar have a chance to see those questions and hopefully the answers. If not by the time period that we've got here to relay them back, certainly we will make them available if people wish to know more about them. But thanks to Jonathan Martin of the NWS, who posed a very interesting question to TWI, and thanks to Steve Dodds actually giving the answer pretty quick. There seems to be a side communication going on. But John raised the question about the fact that he was unaware of seam welding to join the two copper sections along the longitudinal axis, and asked the question, how successful was this work and how was the resulting canister in terms of 100,000 lifetime requirement basically come to fruition. Cutting through some of the nice wordity that Steve responded, basically TWI have recommended exploring alternative to these building up approaches, and stakes are so high and long and expensive with some of these programs. There are some areas that they feel that they could go further with, but again, lots on the NAGRA website, and they basically told us that they are exploring this in depth. And what's really encouraging is, and I'm very proud of TWI as well to be associated with them, that NAGRA requests TWI to write their reports and have theirs, the reports peer reviewed and forwarded on to the regulator as published. So they're in that information's in the chat. Thank you, Jonathan, for raising the question, and thanks to Steve. Yes,
Steve, can I tidy up the answers a little bit?
Please.
So the two paragraphs are not the same customer. So,
right.
So the information on the seam weld, to my knowledge, is not public knowledge, but we were able to show that it was done because we were able to show that picture. That was not NAGRA, so that information will not be with NAGRA. But we'll ask Jonathan. We'll ask our client if they're able to share that to the community. That's up to them, and we'll see what we can get you. But yeah, we often look at doing things like that, even for big aluminium pipes, when we're relying on, at the moment, quite large Russian presses to do stuff in 7,000. We look at different ways of segmenting the pipe, and it's proven useful for EB and friction welding, actually. So happy to explore that with you. Thank you.
Thank you, Steve. Thanks very much for clarifying that as well, because this is a recorded event and we want to make sure that we actually do get the data spot on. I've also asked a few questions for our PhD researchers as well, and the question I posed to both Arij was related to a crossflow designs used. Is this a standard technique? Is it something you've incorporated from a standard, or is it unique? And could this technique that comes from determining your data be standardized or even put into a specification later on? Don't know if Arij is still with us.
Still here. Yeah, so this is I think it can be standard, can be patented, because it is something that I did come up with by myself. I haven't seen it been done before. So the intake duct that you saw before, that was something I came up with using a conformal mapping to solve Laplace's equation around it, and in the end I went with a hyperbola. So that shape that you see is actually a hyperbola, and then on the other end that pump has been inserted into something that has almost a parabolic shape. So I've just used some conic sections to come up with that. So yeah, it could be standardized, I think.
That would be fantastic, because I think what we need to do as the advanced manufacturing community, as well as the other disciplines, is if our researchers are creating something totally unique and has the opportunity to be patented, then that's great for the GDF concept. It's also great for the individual researcher. It's great for the university as well. So keep up the good work on that one. That's really interesting. But definitely approach your patented department.
Thank you.
You're welcome. Thank you. And I have a question for Matthew as well. Is there a need to tune the laser wavelength for particular materials if these are, subjected to such sensitivity? And how would your work function on a metallic composite component stroke product form?
Yes, great questions. The wavelength can certainly be tuned to optimize the process. It's all about absorption to create heating. And what you don't want to be doing is reflecting the vast majority of the energy that you're putting into that system. So we've worked with, for example, copper before, and copper is highly reflective to, I believe, the infrared wavelength that we were choosing, but it's sometimes hard to decouple it from our green laser, which we're using for detection as well. And that's also a choice of frequency there. So definitely both of them need to be highly justified when you have a specific inspection challenge. When we look at just an example, a fair amount of applications have been made to epoxy composites, carbon fiber reinforced epoxies, where obviously there's not a metallic component there. There's the graphite fibers, but they're embedded in a polymer matrix. And depending on your choice of infrared generation frequency, you can actually select that optimally so that it's selectively absorbed by the fibers rather than by the matrix, and that allows a degree of subsurface sort of burying of the source. It's now not a surface expansion, but a buried expansion of material that's generating these acoustic waves, and you get different directivities of emissions, sometimes much preferable directivities, more rounded directivities, emitting ultrasound in every direction rather than in sort of shear lobes generated at the corners of the sort of thermal stress pattern. So that's all a very sort of well understood process, but it's definitely something that for a bespoke application you want to optimize. And as for a metallic composite, you definitely see scattering from the presence of different, say it's ceramic phases inside the composite, or other phases distributed. Just the boundaries between those phases will scatter ultrasound. But that's not to say that if they were finely distributed enough, you couldn't choose lower wavelengths, lower frequencies to sort of ignore them and search for larger defects selectively. And laser-induced ultrasound has the advantage of emitting over a very, very broad band of frequencies. So you get both low frequency vibrations as well as very, very high frequency emission. And so you can filter your signals to selectively look at the high frequency returns and the low frequency components as well, and see a variety of things.
Thank you, Matthew. Yeah, well, you certainly know your subject. So there's something that definitely needs to be captured again. Like Arij, there may be patented material in there as well. Richard, I have one more question for TWI, but I'm conscious that I'm the one asking questions. If there's anybody else who would like to ask a question, please feel free. We've gone 4 minutes over, but the material that was presented here today is so vast, and I just want to make sure that people get the opportunity to ask. Well, I'm going to jump in and then just, Steve, it wouldn't be right of me not to ask TWI a question. With your work, the excellent work you've done on electron beam and friction, what are your thoughts of incorporating these technologies within a hot environment, considering the effects from radiation on processes and tooling systems? Do you have any thoughts about that?
We have quite developed thoughts on that, because it was a conversation we were having just last week, because that's how real everything's getting on this now for some of the programs. The answer is lasers are difficult in that. So just as a general overview of manufacturing technologies, lasers are difficult. Friction stir welding is well received because you can do it at quite a long shank distance, and it's quite simply mechanical. However, for the particular project we're talking to, it's 50mm partial pen, and they really want to do it with electron beam. Now, the electron beam reduced pressure is useful for the size of the object and the glove box environment that we're talking about here. But if you remember at the start of the presentation, I said it requires a short standoff distance because you get beam scatter with the reduced pressure. So that's the challenge, is trying to get as close as you can whilst keeping the electromagnetic manipulators far enough away from the hot zone. So great question, Steve. Looking forward to telling you the answer in a few weeks' time, but or at least the plan in a few weeks' time. So yes, a very big challenge. Yeah.
Excellent. Thank you, Steve. Thank you very much.
I can probably add to that questions about the probabilistic stuff. So just very short, a very short comment. So the as far as any analytical work is concerned, any assessment work is concerned, when it comes to machine learning, you need huge amount of data, and then with more of these exotic welding techniques, companies are not ready to share data like defects, because they don't want to market that they are making defects in the wells. And then it's only with huge amount of data that you can establish an interdependency between each element. It's no point getting an empirical model into machine learning, because you're basically using the same model to generate the same result. So that is pointless. So my advice is that if we are going to push through more reliable, accurate machine learning, then that has to come from direct testing.
Thank you, Yin. Yeah, thank you very much. Brings us back to the recent structural integrity discussion on modelling. So I think I saw a hand from Charles.
That's me, Steve. Yeah, just to add to what Steve Dodds said about considering effects of radiation, that's clearly a concern for the inspection methods that are chosen as well. So in a radioactive environment, you're obviously going to be concerned about fogging of the radiographic film. So that's why we're led towards ultrasonic inspection technologies, and also you have to be careful about your use of couplants in that situation, or choose a non-contact method where you might be concerned about signal to noise. But also for surface methods in those environments, if you can, you want to avoid anything that involves consumables or cleaning the surface, like you might have for penetrance or MPI, and that's why we tend to be drawn towards eddy currents or eddy current array technologies. So that's some of the background to the choice of NDT methods, particularly for that closure weld situation.
Thank you, Charles. Thank you, Yin, and thank you, Steve. Yes, I definitely think there's something that TWI and others should be pushing for maybe some lower TRL research, EPSRC, etc. But further discussion. Conscious that we're 8 minutes over, but what a great presentation. We've had a lot of compliments from people who have had to leave. So just once again, on behalf of the NWS RSO Advanced Manufacturing community, thank you very much for your time, your efforts, and we look forward to seeing what this comes out like on YouTube. So thank you very much and have a great weekend.
Thank you. Thanks, Steve.
Bye-bye.
Bye.